the law or the principle, then carry on asking you questions, right? So then we have something else. So this is the easiest, something that you should never get wrong, which is power. You can't get it wrong. So power, amandla. Power is the rate at which work is done. What does this mean? It means if we have a box here, and we pull it for 50 seconds straight, we keep pulling this box, we now have time, which is 50 seconds. So power is the rate, time. This is what you have here. At which work is done is the rate at which work is done. We've got work here, which is our W. So therefore, power is the rate at which work is done. So that means work over time. How much work have we done in 50 seconds? Right? So this is what this thing is saying to us. So we can move. When you see work, they will give you time at most. Sometimes they won't give you. I think you can use there are those formulas that you can use to get time. So it's not bad. You can understand it, right? So let's go back now and try to do some examples from work, right? So I'm gonna start with a simple example for those that joined late. Let's start with a simple example so that you can see what we're talking about. At the moment, we have this box here. Our box is 10 kg. Then we've got the applied force here, which is going to be 600 newtons. This is on the rough surface. How would you calculate your power? Right? So the way you would calculate your power is the same way. We already know what is power. We already know the formula of power, not power. So not power, work instead. So we've got work here, got force, displacement, then cos theta. Right? So here we've got friction. We also got this here, applied force. So that means we've got a force here that is pulling back, which is our frictional force. Let's say Fk, kinetic friction. And then this box decides to move, this time 15. It decides to move 15 meters when it gets pulled, right? So make sure that your units are always the correct units, because if they are wrong, you're going to get wrong answers. So please make sure that your units are always correct. So that means here we're going to have work done by friction and then the work done by the applied force, right? Work done by applied force is going to be the positive work. What about the work done by friction? Is it going to positive work or negative work? Okay, it's going to be negative work because it's going into the opposite direction where the box is going. So the box is going this way, and you find friction is going the opposite way. So it becomes negative work. Okay. So in this case, we're going to have work done by frictional force, which is equals to frictional force times the displacement cos theta. Theta is the angle between this surface here and this force. And the angle between them is 0. Right? But if we had something like this, it wasn't going to be 0. Okay? It wasn't going to be 0. So you can easily just substitute here whatever you have. Sometimes, but let me like make it a bit nice. Sometimes they can give you and say, we've got mu k as 0.1. Calculate the work done by friction. They've not given you a friction. So we know that friction is equal to mu k times normal force. So then you can do the honors of calculating this. You already have this part, you just need the normal force. And we know the normal force is equal to mg, is equal to weight in this case, right? So that means going to be 10 times 9.8. That is 98 newtons, right? Then you come here, you substitute. You've got Fk, mu is 0.1, then you have 98 here. Then you're going to have your answer for Fk, right? 0.1 times 98 becomes 9.8 newtons for our friction. But then what is the work done by friction? So the work done by friction now would be the friction itself, this 9.8 newtons, times our displacement, the box is moved 15 meters, cos what is the angle between the surface and the friction is 0. So put 0 here. Then you're going to have your answer here, right?
147.
147 joules, right? Sometimes they can write it as Newton meter. The meter comes from here. This one is in meters, This one is in newtons. So it's Newton meter, right? So, but then it can happen sometimes that they come to you and then they'd be like, okay, seems like you know it. They give you an incline instead. So then you have an incline like this. And then you have your theta here, which is equals to 30 degrees. Then you have your force here, which is still gonna be 100. You have 10 kg here. So in this case, they might want different things. They might want work. They might want network. They might want work done by friction, by the weight components and all, right? So let's start with our free body diagram. So in this case, so that we see all our forces, we're going to have a free body diagram like this. You're going to have your normal force here. You're going to have your weight, Fg. And then you're going to have your force here, which is 100 newtons. And then if they say to you a rough surface, sometimes they're going to say rough surface, sometimes they're going to just give you the friction, right? So if they just give you something, then you should know. If they say rough surface, you should expect friction there, unless they give you the friction thing, right? So you have something like that. So that means you would have friction here, which is F K, right? But in a case whereby they haven't given you your friction, sometimes, as I've given you before, they say 0.1. They don't give you friction. In this case, you can't say your normal force is equal to Fg. This is not, it's not gonna work because you're now in an incline. So your normal force is gonna be equal to this component of weight, which is Fg perpendicular, right? Then you can calculate your friction. So if I can add the components for you, let me just move this Fg, put it this side, and then gonna have this is your Fg parallel. It's parallel to this surface here. That's why we say Fg parallel. So let me put my theta here. Then I can get my Fg parallel and my Fg perpendicular. So we are interested in both of them because we don't have, you only have this. We need to calculate our Fk, which is like this times normal force, right? We need to calculate it. And this normal force now, this normal force is equal to Fg perpendicular. And then we can also have work done by this force here as it's going down, right? So the number of works you can have here is this work done by G parallel, done by Fk, then done by this 100. Okay, please calculate this for the next 5 minutes. Then we come back and then we see if we are understanding or not. I'll wait for you here in 5 minutes. So that means in 7:31. Okay.